Hi, and welcome back. Now, the previous two videos that you watched gave you a historical foundation and started you on a mathematical foundation for physics. Today's lecture is the first in a series of three designed to help further develop your mathematical foundation. The topics of these three lectures are going to center around the idea of the vector. Now, in my experience, at this point in your mathematical education, if you have not had Calculus 3, your experience with vectors is relatively minimal. Perhaps you saw them in a trig class. Somebody said, yada, yada, yada. Oh, there's this thing called a vector. And then, that was the last time you saw it. Now, the truth of the matter is that in physics, vectors are incredibly important. We use them all the time. Now, so like I said, most things that you're familiar with up to this point are regular numbers. For example, 20, 55, 191.2, minus 12, and whole numbers or decimal numbers that are just numbers, even though they might have a unit, are called scalars. They represent the size of something. They represent a value of some sort. Positive, negative, decimal, it doesn't matter. Now, vectors, on the other hand, are special. Because a vector has a size, and it also has a direction. Now, because of this, because it's not just a regular plain old number, the mathematics of vectors can be pretty complicated, which is the reason why we have 3 lectures on just vectors. Now, that said, the rules that you know of dealing with scalars are the standard rules of algebra. Now, I'm sure you may vaguely remember some of the properties of algebra. For example, numbers in algebra commute, they distribute, they associate. We also know that you have a zero that exists, such that if you were to have a number, we'll call the number A, and you added 0 to it, you would get A back. There is a such thing as a 1, such that 1 times A is A. And you also have an inverse. An inverse is such that when you multiply it by that, you get 1 back. Now, mathematically, all these things are easy to deal with. You can multiply 2 numbers together, whether you multiply the first times the second or the second times the first. If you add A plus B, it's the same thing as B plus A, all these sorts of stuff. Now, that said, vectors also follow the rules of algebra, but the way they follow the rules of algebra can be a little complicated. Now, that said, let me draw you an example of a vector. This is how we typically represent them. It's a straight line that has an arrow on the end. That's a vector. Now, I'm not very creative, so I'm going to call this A. So this is a vector. And the way you would represent the magnitude would be through the length, because magnitude is synonymous with size or length. Now, lengths and sizes are always positive numbers. And because of that, the magnitude of a vector is always positive. So, one thing you can remember, the magnitude of a vector is always positive. So this right here would be the magnitude, its length. Now the direction that the vector is pointing is the direction. Now, that said, to start us on our journey of understanding the algebra of vectors, what I would like to do is to look at the classic way that vectors were added to each other. Now, that's called the method of parallelograms. Now, back in the day, before people had really nice calculators that could bust out, sines, cosines, and tangents with no issues at all, many times, in order to deal with vectors, people would add them graphically. So, let me give you a sense of how this might work. So, here's one vector right here. And I'm going to draw another vector. Let me use a different color just to be different here. Here's another vector that maybe goes this way. All right. So the way that you would represent adding these things together would be the following way. You reproduce the vector, and this is at 45 degrees. Let's see, 1, 2, 3, 4, 5, 6. So from here, 1, 2, 3, 4, 5, 6. So that's a mirror of this one right here. And this is a mirror of that one right there. So let's give these guys some names. I'm going to call this one A and this one V. Oops. Oh, that's interesting. Didn't know we would do that. Now, the way you would visualize adding these things together would be to simply cut the parallelogram in half along the long way. So here, for example, let's get a third color. I'll go with this sort of hot pink right here. That looks interesting. This would be the, well, doesn't like that, does it? All right, you're a problem. Let's see if I can do this a little bit different way. Yeah, where's your problem? Having a hard time doing this one. Takes all types, huh? Well, I'm going to freehand it. Don't laugh. Let's see how badly I can do this. Why is it trying to... It's trying to go along there. There we go. Look at that. Awesome. This would be this thing cut in half, and that right there would be A plus B, right there. Now, look, really all you've done is to take the tail of one vector and put it at the head of another. So another way of looking at this, about thinking about adding these two vectors together, would be the following way. You take vector A, oops, I'm getting used to all this. We'll start with actually vector B. You take vector B, This is 7 over 3 up. Yeah. There you go. That plus that is equal to, hopefully this is going to work for us now. Gonna get it close. Gonna get it close. Oh, it's so close. Oh. Let's pretend those tips lie right on top of each other. So, this is ridiculous. All right. So right here, this right here would be B. This would be A. And this would be A plus B. Or B plus A. I want to prove that to you here in a little bit. Okay. So the method of parallelograms basically has you make a parallelogram out of your two vectors by kind of completing the sides. And then when you split it in half, that's the visual representation of adding those things together. Now, if you want to think about it in a more practical sense, let's pretend these vectors represented directions that you walked. So you start out here. Let's pretend that you walked 30 feet this way. You stopped. You turned to the right a little bit. And then you walked an additional 20 feet this way. So walking from here to here got you from this point in space to this point in space right here. So that's a graphical way that you can think of adding vectors together. Now the reason why I want to do this is because the method of parallelograms is an easy way to visualize what it means when you add these things together, but it's not very useful from a physics standpoint. And that's because it's hard to associate these things with real physical quantities without having a point of reference. And by point of reference, I mean a coordinate system. So let's go down over here. I've got a coordinate system that I've drawn out for us. And let me draw a vector and show you how we visualize it in a more mathematical sense. So let's pick a fun color. Go red this time. From here, here is our vector, I don't know, something like this, we'll say. There. So I'm going to call this vector C. Now, look. I walked from here and ended up there, if you want to think of it like that. One way I could get here, if I was only allowed to move along the X and the Y direction, would be to walk from here to here and then walk from here to here. Now, as we saw on a previous thing, walking from the tail of one arrow to its tip and then from the tail of the next arrow to its tip is the same thing as adding these things together. So here, if we call this CX vector and this CY vector, then it must be true that the vector C is really just X plus Y. Now, the reason why we're limiting our motion here along the X and the Y direction is because what I'd like to do is to relate this back to trig. Now, I know trig is a dreaded word. It's incredibly necessary for physics, so we're going to have to deal with it. Now, here in a coordinate system, if you vaguely recall, your experience in trigonometry, you reference directions in the y direction or in the x direction with things that are called unit vectors. So, for example, you may have seen I hat, j hat, and k hat before, depending on how far you've gone into the calculus, or depending upon what kind of instruction you had back in algebra or even in your trigonometry. Basically, these things relate to x, y, and z. Now, to make our lives easy, what I'm going to do instead is I'm going to use things a little bit more intuitive. X hat, y hat, and eventually z hat. Okay? So when I say x hat, all this means is that I'm moving in the x direction. When I say y hat, all that means is that I'm moving in the y direction. So if you think here of the length of this vector as being cx in the x direction, and you think of the length of this vector right here as being cy in the y direction, then one way you can visualize writing C is that it has an x part in the x direction and a y part in the y direction. Now, this right here is one of the most common types of notation that you see used in physics for vectors. So you might want to remember it. All right, so let's do an example. Let's see. Let's get us a little arrow here. We'll do orange this time. Actually, let me stick with black. So here's another vector right here. I'm going to call this one A. Now, we've drawn this thing with respect to a coordinate system, which means that we can talk about its pieces. For example, its x part, we call that the x component, and its y part. Now, we can also talk about the angle that it makes with respect to the x-axis. And in physics, much like mathematics, the axis that we use for reference most of the time is x with respect to angles. Now, just as an example here, let's pretend that our vector here had to do with distances that you were walking. Now, how far did I walk from the origin of our coordinate system right here to the tip? I don't know, 20 meters. What angle does this make with respect to the x-axis? I'm just going to make something up here. I don't know, 15 degrees. Sounds good. Now, what I'd like to do is to find the components of A. That's what I want to do. Now, how we're going to do this? Well, we're going to refer to our friend trig. So, as a reminder, from oh so long ago, you have your three basic trig functions: sine, cosine, and tangent. Now, sine is defined as opposite over hypotenuse. Cosine is defined as adjacent over hypotenuse. And tangent is defined as opposite over adjacent. Now, if you look at where this angle is, and you look at, whoops, makes sense, should have drawn that in the correct direction. And you look at the pieces that make it up. This right here, in this particular case, is the part that's opposite of the angle, and this right here is the part that's adjacent to it. This is the hypotenuse, because after all, this forms a right triangle. So, sine, for example, relates to the sides of our vector right here, or the components of our vector, the following way. It's AY over A. Cosine AX over A. And tangent AY over AX. Now, the goal is to find AX and AY using what we know. And what we know here is that the hypotenuse, the magnitude of our vector, is 20 meters, and the direction that it points is 15 degrees above the x-axis. So, if I look here, and I look, we'll say, at the opposite part, if I do some simple algebra, that would give me the opposite part. You plug your numbers in, make sure your calculator is in degree mode, and if you do the math, you should get something that looks a little bit like, I don't know, 5.18 meters. Now, if you look at the adjacent part right here, that's here, cosine. And you do the math on that one, and you're going to get 19 about 0.31 meters. So, what are the components of A? Well, the x part is 19.31 meters long. The y part is 5.18 meters long. Now, how would you express this vector in components? Well, AX, x hat, plus AY, y hat, 19.31 meters x hat plus 5.18 meters y hat. Now, if the numbers seem a little bit weird to you, we can always check, because we can use the Pythagorean theorem. So it should be true that if I go back and find the length of this and find the angle it makes with respect to the x-axis using these numbers that I found right here, I should get 20 meters and 15 degrees. So let's just check ourselves to make sure. So the length of this vector should be, like I said, 20 meters. You take the square root of the sum of the squares. And let's see here. Plug this into my calculator. Doop. Square root of 19.31 squared plus 5.18 squared. $19.99. And considering that I had rounded these numbers right here, yeah, that's 20. Let's check the angle. Well, according to this, that angle should be the inverse tangent of AY over AX. So let's see. AY, 5.18 meters. AX, 19.31 meters. Let's try it. The inverse tangent of 5.18 divided by 19.31. 15 degrees. So it checks out. So you may have been given the vector originally in a form that looks a little bit like this. But from a physics standpoint, it's really only useful when you can break it up into components. And we're going to see why in a minute, basically. All right. So, before I go further, let me make some copies of this just so I don't overstay. Welcome to this. We'll place another one down here just in case. There. All right. So it's a pretty easy example of simple breaking things up into components. Let me do another one here. So, why don't we do one that's a little more complicated? Like this. This angle right here, 120 degrees. I'm going to call this vector right here C. It has a length of 120 newtons. Now, this part right here would be the X part. Now look what direction it's pointing. It's pointing down the negative number line direction. All right. This right here would be the Y part. All right. I'm actually going to make our life easy, put that over here so it doesn't get in the way. There we go. So that's the Y part. So X, Y. Now, there are two ways that you can handle this. The first way would be to just blindly follow our way through trigonometry and let it do its job. The more intuitive way, which is the way that I urge you to do, is to try to keep your angles that you deal with under 90 degrees and then use common sense to decide directions. So this is 90 degrees, this is 120 total, and what that means is that this right here would be 30 degrees. I'm going to call this theta sub C. All right. Now, so if this right here is my angle, and I write out my trig functions like this. Sine, remember, is opposite over hypotenuse. The side now that's opposite is the x direction. Cosine is adjacent over hypotenuse. Y is adjacent. Opposite over adjacent, just like that. Now, I want to find the components here. If you use your sine and your cosine here and you do some simple algebra, Cx is going to be equal to C sine theta sub C. Cy is going to be C cosine theta sub C. So if I plug the numbers in here, nope, I didn't want to do that. Oh, I was going for 15. So you actually do that. You should get 60 newtons for that. And for this one, something that looks like that. Okay. So what I'd like to point out here is that we can't forget that vectors have magnitudes and directions. So if I wrote out my vector as just cx x hat plus cy y hat, and just plug these numbers in, what I would have would be a vector that had a positive y part and a positive x part, which means that it would be pointing somewhere over here in this quadrant right here. But as you can see here, the y part points up, the y direction, the positive y direction, but the x part points down the negative direction right here. So to correctly account for that, the x part has a negative sign in front of it. And that is one of the first real lessons. Vectors, negatives mean things. They have a directional part. Negative means down the negative direction. So the way you would express this would be minus 60 newtons x hat plus 103.92 newtons y hat. Now, you can check it if you'd like. It should be that when I take the square root of the sum of the squares, that I get the original thing back. And let's see. Put this in our calculator. Minus 60 squared plus 103.92 squared, 120. It's 119.997. Again, it's a rounding thing. So you get 120 back. You want to check our angle right here. We have to use our inverse tangent. Now look over here though, instead of it being y over x, which is what we're usually used to, it's going to be x over y. And I guess this should be theta sub c. It's 30. There you go. So it works. So the takeaway here is that in order to do something useful with a vector that we've been given, you can't just operate from, a number in a direction. 120 newtons at, 120 degrees with respect to the x-axis. That isn't sufficient to directly work with. We're going to need to break it up into pieces. Now, that said, the next big thing that I want to discuss is going to be addition of vectors and some parts of multiplication. And we'll pick that up next lecture.